Xian Li is a six-year PhD student in psychological and brain sciences at Johns Hopkins, where she works with Janice Chen and Christopher Honey. Her research uses behavioral fMRI methods to understand how the brain organizes real-world experiences in memory. Today's talk, titled Human Memory in the Real World, Dual Pathways to Maintaining Mental Continuity, explores how we stay mentally connected to ongoing experiences, even when interrupted. Yeah, let's welcome Xian.
Thank you. Can people hear me all right, right? And I don't sound crazy loud or okay, cool. So I have a couple of projects throughout my PhD which explains why I'm doing 6 year instead of 5 or 4. But this project that I'm gonna be talking today is as have been introduced. Neural pathways to maintaining our mental continuity. And I guess first I'll have to explain what do we mean by mental continuity. If you imagine like two people talking, you can go down a conversation layering more and more complex contexts so that you understand a gossip precisely over its correct history. And in real life, you talking with ChatGPT, you'll feel that sometimes we've continued on with a topic for quite a while. So if you had brought up with a new topic just slightly for another information, then after that, you go back to the previous context, to the previous topic. It should be obvious that you're transitioning back, but GPT doesn't seem to consistently understand which topic you're transitioning to. And so, to understand that, and to put that in a concrete scenario that we can test in a lab space, we can imagine a situation where you're reading a novel, Harry Potter book, say chapter number 10 down the road. You already have a very complex understanding of the magic world of Harry Potter's relationship with his friends, with his enemies, with like the family history and the entire world background. So when you're reading a sentence at the current chapter, you're not just understanding that sentence in isolation of seeing that sentence and understanding that sentence alone. You're understanding that input given against the entire context that you have built up over the past 10 chapters. So, when you're immersed in that narrative reading and poof, your mom pulls you out and say, "Hey, why is my phone not making any sound? Come check my phone and do the setting for me." I don't know if it happens to you, but it happens to me. So maybe it doesn't take that long, just like 20 seconds or 30 seconds to set up some stuffs on her phone. And then you're back again to the story. Now, the question is, how do you preserve the continuity of the previous complex context that you have set up? Because you need to understand, you need to pick up where you left off, which requires you to have the correct entire context. And therefore, the question is, how do we access the previous mental context? There are existing memory theories that we can provide some predictions. First, there is the hippocampal-based long-term memory encoding and retrieval. We know that hippocampus is important for long-term memory storage, and these group of theory would probably posit that at the onset of the interruption, you will have a hippocampal encoding. And so later on, when you come back to the story, you will retrieve it from your long-term memory. So you don't have to retain anything during the interruption. In the meantime, there are contradictory empirical findings in the field. For example, hippocampal amnesic patients, they don't have intact hippocampal structure. The entire medial temporal lobe is lesioned. So in these group of people, you really don't expect that they are sensitive to a long history window from the past. So if you're reading the current sentence, you probably should only be sensitive to the information of the current sentence instead of its entire context window from distant past. However, this is not the case. This previous study observed default mode network, a set of connected network that is observed to commonly fluctuate during the resting state. These networks show long history context dependent for processing the stimuli of the current input, which means that they have certain amount or some format of memory from their past. So how are they able to do that without their hippocampus? And the working memory people may say that we all know that the dorsolateral prefrontal cortex, the DLPFC, is the classic center of working memory. So this set of theory may say that, hey, maybe during this interruption phase, even though you're helping your mom to set up her phone, you're actually actively rehearsing in your working memory, sustaining an activity trace or activation pattern through the interruption, like how you're rehearsing a number back and forth, so that you can keep that pattern throughout the interruption for your later return to the story. Now, I'm already showing the contradictory finding here, which is the studies have reported uncontrolled lingering thought of the story, but working memory information maintenance requires active control and effort to keep it in place. So when it is out of control, it doesn't seem to satisfy a working memory requirement. And with those two off the table, somewhat off the table, perhaps there is a continually updated context representation that can be sustained through interruptions in a somewhat passive or autonomous way, so that it doesn't require your active control for your working memory's required central executive to put it in place, but rather it just self-sustains itself. So this being the proposal of the study, we have to design an experiment to address it. We had people lay inside of the fMRI scanner and listening to an audio story where annoyingly every now and then we interrupt them in different kinds of ways. Each interruption is 20 to 30 seconds, which way exceeds the duration of classic working memory's 10-second long range. And each story segment is 30 to 50 seconds. We cut the story into 18 chunks, and this is a pretty engaging murder story that is already demanding to understand the complex relationship between the different people and what has happened and who is potentially the murderer. And to observe the continuity of the mental context, we need to open up observation windows such as this, with the gray shaded area being silent pauses. And this is what we call an intact story with intact sequence being presented and pause interruption, intact pause. This is to open up observation windows so as to observe any neural representation that is associated with the mental context. Now, I'm going to just go on with this condition to give you an intuition of what the signal looks like. So this is the A1 plus, which is the primary auditory cortex in the human brain, its main bold signal, which represents the overall activation in the primary auditory cortex across the entire phase of the 18 story segments, which gives us 17 interruption epochs. And you can see the big dip every now and then, which corresponds to the silent pauses, because the auditory stimuli is removed, and so you see the big dip. That being the onset and offset of the story, and we can zoom into one interruption epoch so as to see its correspondence to our design of interruption for story, with the onset of interruption, offset of and return to the story. With that being the global signal, with this being the primary auditory cortex signal, we can compute the inter-subject synchrony in their time course by computing the Pearson correlation R value of this time course for one subject versus the average time course of the other subjects. And we can do this for each area in the brain, which gives us this whole brain intersubject time course correlation map. So this is for quality control check. We're only doing this to make sure that the signal looks good, that the brain response replicates the previous literature, and that everything is as designed. And what you can see here is a big lit up across the MSTG, the medial superior temporal gyrus, this strip, with the primary auditory cortex here, and they're the most lit up in the language area processing for auditory stimuli. And then comes the DMN area, DMN-A and DMN-B, like with the medial prefrontal strips. And so these are the typical areas that you would expect for people time course to sync up when they're watching a movie or reading a story, doing narrative processing. And now this is just to give you a sense of what the data looks like and to confirm that the signal is good, our manipulation is successful. So we can continue to introduce some other experimental conditions. Do people have questions? No? Everything's good? Okay, cool. That being the main experimental condition, we have a lot of other conditions to control for different confounds. First, how do you know that when people come back from an interruption, that their signal is being unaffected from the interruption phase, that they're still continuing to understand the story as they should? To control for that, we need to have a ground truth where we have a continuous group of subjects which listen to the story in continuous fashion, and their neural representation pattern at each time point served as the answer key, the ground truth, if you will. And now another critique could be that, hey, during this silent pause, you could be recruiting your working memory. You could be doing active rehearsal, which requires central executive. So you already have that in working. So maybe you don't need a passive contextual representation to be sustained. How do you address that? So to address that, we have another condition, which is called intact story theory of mind interruption, where we have the same presentation of the story and the interruption structure, but with the interruption phases filled with a story irrelevant theory of mind question. And these are questions like, Mary and Tom are at the beach. Mary went swimming when Tom was asleep. When Tom wakes up, when Tom is still asleep, Mary decided that she's tired from swimming and wants to go to the mall. She checked on Tom and made sure that he wasn't awake, so she would go to the mall and try to come back as soon as she can. When Tom wakes up, Tom did not find Mary in the scene. Now, question, does Tom know that Mary is at the mall? So this is to give you a sense of what these questions are like. They're like a separate situation that people need to assemble in their brain and try to understand who's with who and who did what during when, and then answer a question related to this situation. This is to take up people's working memory so that it is not recruited for rehearsing the story relevant contexts and features. So this is to divert people's working memory. In addition to these two controls, we have another control to address another potential confound. So if we found this passive episodic background-ish context representation, how do we know that it is relevant to the story's context without being just a drift of the neural signal across the story? To address that, we have a separate experimental condition where we scrambled the entire story in sequence so that people listen to it's like random scrambled sequence of the story, which is really hard to piece together what had actually happened. And so this is to take away people's understanding of the entire narrative's mental context while still preserving the local neural representation for the ongoing stimuli. And with this, this is to disrupt the formation of mental context. And so whatever neural evidence we see in the intact pause, we do not, that builds up over time, that evolves over time, we do not expect to see it in the scrambled pause, so as to call it a mental context. So these are the experimental conditions. And do people have question on this slide? Because I know that we have attacked ourselves when we designed the experiment in different ways, and that's why we came up with all these different conditions. Yes, I see hands. Please.
Okay, hi. I just want to know that in IP and SP condition, is the interruption just a silent pause, like with nothing happening?
Yep, exactly.
Okay, thank you.
Any other clarification questions before we move on? Nope. Okay, cool. Then let's look at our regions of interest because there's 400 parcels for the Schaefer Atlas that we used, and we need to predefine our regions of interest. First, the auditory and language areas, such as the A1 plus that we just saw the bolt signal for, and the medial, the MSTG for subsequent language processing, and classic working memory area, the DLPFC, as well as the hippocampus and amygdala, and nucleus accumbens and striatum for reward-related, memory-related supports. And as to our candidate areas for a mental context support, angular gyrus and anterior cingulate cortex, bridging a bit with the DMPFC, which is also relevant. There's PCC and dorsal parietal medial cortex in the medial view, in the medial wall, that are some of the most likely areas that we expect to see a mental context related representation. So these are basically the angular gyrus, and this column are the actual ROIs for our proposed thing, and the other areas are for auditory and language processing and long-term memory and working memory related areas. So if that is clear, we will move on to talking about predicted neural signatures. For long-term memory, we previously said that maybe there is encoding, hippocampal related encoding signal at the onset of the interruption, which could predict individuals' memory for the narrative. And so even when the interruption phase weren't, it's like have had your working memory diverted to elsewhere, you wouldn't care because your long-term memory already has that information. So when you return to the story, you can just retrieve it. The working memory hypothesis would be that throughout the interruption phase, you have your DLPFC activity or activity pattern sustained so that the neural geometry associated with the narrative context is being well preserved through the interruption so as to smoothly return to the story. So this is to say that dorsolateral prefrontal cortex actively sustains a trace. And then eventually for what we proposed for a missing neural representation, a passive trace that is sustained through the interruption in some form of DMN activity or activity pattern that even works when your working memory is diverted to elsewhere. So this is to say some DMN spontaneous trace. Now, what does the result actually look like? corresponding to hippocampus, we saw a significant hippocampal activation at the onset of the interruption, and you can see that for each of the three interruption conditions. Now, if you remember the three interruption conditions that we had two silent pause interruptions, which is the intact story pause interruption for the blue line, with the green line being the scrambled story sequence and pause interruption. And then for the orange line, this is the intact story, but with theory of mind interruption. Well, this is the overall group averaged hippocampal signal. We can do this averaging across these number of TRs during the interruption onset to minus the baseline pre-interruption for each individual subject, so as to get an estimate of, on average, how does a person's hippocampal activation rise up at the onset of the interruption phase. And with that, we can compute its potential association with this person's memory for the narrative, or overall percentage of event recalled for the story. And there is a significant correlation between the two variables, which means that, yes, hippocampus is working. It predicts your individual memory on a person-to-person basis. But here you might already notice something. There are three interruption conditions, two of which are pretty disrupted, and one is pretty undisruptive, which is the intact pause condition, the blue line. This group of people has the best hippocampal signal, the increase. And how come this is the group of people that you don't see hippocampal activity predicting individual memory? Now, I'm going to leave a suspension here for the later neural signal that we found that does account for their individual memory. But here, the take-home message is that hippocampal activity did increase at the transition at event boundaries, which predicted individual memory. But it only predicted individual memory in the more disruptive conditions of interruptions. Whereas in the intact story, silent pause interruption, you saw a good hippocampal rise signal, but they don't predict individuals' memory for the narrative. Any question on this slide? Straightforward? Cool. Right. So, with this being the case,
I think we have a question.
oh yeah, go ahead.
Can you hear me?
Yeah, very vaguely. It's kind of hard.
Can you hear me better now?
Oh, way better.
Okay. I was wondering if you can explain more about the baseline. I'm not sure that it, did you get that? Is that before the story was told, or was that?
The what? Sorry, the sound came off again.
Hi, could you hear me?
Oh yeah, way better, way better.
Okay. I was wondering if you can describe more about the baseline, if that was before the story was told, or because so this increase is told when the story is told. So is the baseline, was there like
Oh,
a
yeah,
period of
good
before the
question.
story? Yeah, just
I was hoping for clarification questions like that would come up so that I can, because this is a complex design and I totally understand that I fly through things a bit too fast. But if you remember the gray shaded area in earlier design plot over here. The gray shaded area is the interruption phase. So the blue segments are the story phase where people are listening to a story. And into the interruption, there's silent pause. So the A1 dropped. So corresponding to over here, The baseline is just before interruption happens, they're still actively listening to the story. And so hippocampal has like pretty noisy zigzag shapes across different individuals. So when it's averaged across individuals on a group level, you see this like relatively lenient looking like waves of activity around baseline. And baseline is around 0 because we z-scored the time course based on the story phase. So the baseline is the story phase activity variations. And then the gray shaded area is when the interruption starts to occur. And so in the audio story, you would hear, so the man takes away the shield of the blah 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 blah, and then they came to the park to blah 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 and do something, and then the audio pauses a little, and then you hear beep boop. So that's the audio cue for people to know that, oh, it's an interruption. So followed by long silent pauses until they hear beep boop again, and then the story returns. So that's the actual it's like audio experience that people go through, which corresponds to over here, which is before the beep boop sound happens at the transition 0. And we're just taking the previous 5 TRs, which corresponds to about 8 seconds, because each TR is 1.5 second. So this is just to quantify how much neural signal has risen after you transitioned to using the baseline of the story. Did that answer your question?
Yeah.
Wonderful. Any other questions? Like questions for why would hippocampus be so activated when they're listening to silent pauses? If people are not like curious of that, then I will just move on. But if you want to know.
You can go.
Hi. I'm just wondering what is that R value in the graph mean?
The R value. This R value. A good question. Because I know it's confusing. I plotted 3 lines, and then the R value is actually concatenated across 3 conditions where you have like about 60 subjects. This is the correlation R value between the vector of 60 people's hippocampal increase versus the 60 people's narrative memory.
And no matter in what condition.
What?
No matter in what condition.
Yeah. This is aggregate across the 3 interruption conditions. If you just focus on these 2 single conditions, the correlation R is like higher than this. Because you can see that this R value is already kind of dragged low because of the flat line for the blue. So even though like the intact Tom and the scramble pause conditions, they only had 20 subjects each, their correlation value is actually still statistically significant. The only thing that is not significant is the intact pause condition. Anything else?
Say more about the memory task, like how you're measuring memory.
Oh yeah. That's a really, really good question, because it took us a very long time to quantify their memory, because these are you can sort of imagine this is not simple word lists. It's not like people say something or not. It's not like a simple categorization. This is actually people inside of the scanner produced verbal recall describing the story in as much detail as possible from whatever they could remember of this story. And so we had a group of raters who went through we first had the audio recall transcribed into texts, and then have the texts be grammar checked with the filler words removed, and then have those segmented into meaningful clause or sentences. And then for each of the recall sentences, we have a separate group of rater read the story and read a person's recall segment and match that segment to which of the events in the story does it refer to. And so that gives us, for each of a person's recall segment, a set of story events that it corresponds to. And eventually, we result in a vector of zeros and ones, a binary vector of whether a story event had been recalled or not. And so you can imagine for a story with maybe 100 events, then you would end up with about like 50% of the events being recalled, or 20%, or just 10% of the story events being recalled. So that is the numbers on the y-axis. This is highest at 50% because it's a pretty long story. Any other questions? All right. So that is our hippocampus. Now, the working memory people may say that maybe you're not seeing the intact pause subjects hippocampus predicting people's memory because during the interruption phase, your working memory is still processing that stimuli. So you have another source that predicts your individual people's memory because of that additional process. And so this is to say that the LPFC is actively sustaining a trace during the interruption. And for example, you would predict the trace to be the mean bold signal, which is just the activity, and which is not the case. Here, I'm just showing the bold signal for DLPFC across the three conditions. And you can see how the theory of mind people, they have like a drastic rise after the beep sound response because they're actually listening to another set of situations that requires their working memory. But the intact pause and the scrambled pause, the blue and green line, they drops over time. So it's not the classic monkey study and the classic fMRI DLPFC activity where you're rehearsing something and you will actually see a rise and sustained signal throughout. So it's not what I would predict for a sustained neural trace for DLPFC. On the other hand, you don't need to have a sustained bold signal throughout the interruption. You can just retain the neural geometry, just the pattern being sustained, even though the overall activation dropped is fine. And is that the case? And that is actually the case in our study. But I'm going to skip the part about how we have the signal sustained measured because the more important thing is not to just have the pattern sustained, but have a pattern about the story that is sustained. So it's important to know that the pattern that gets sustained over here is locked to the story instead of just being a generic state-related neural pattern. For example, you can imagine the LPFC being task on, task off, and then during the task off state, it just falls to another state and stays in that state. And you would see this pattern being sustained through the interruption, but it wouldn't mean anything to us. So it is more important to establish that this pattern is associated with the story stimuli so as to say something about the working memory is being incorporated. Now, that to measure that, how do we know that this pattern is specific to the story segment that comes before it? We do a time-time correlation matrix. So this over here is a gigantic matrix that I expect to receive questions of what it is, but I'll first try to explain it. So here is on the x-axis, one person's neural pattern across each time point. And so on the y-axis, this is the average neural pattern of other subjects at each time point. And therefore, it's called time-time correlation of neural patterns. And each of the cell here, I'm showing one example cell on the diagonal, which is matching time point, TR example number 118, versus the average neural pattern of the other subjects at the same time point. And the correlation R value between these two time points reflects how similar people's neural geometry is between these two time points. So you can see a pretty lit up diagonal strip, which is, I'm just showing the A1 here, the primary auditory cortex, which should have a similar neural geometry for matching time point because they're listening to the same exact stimuli. And so the diagonal lit up is basically a reflection of people's neural geometry driven by the stimuli. Is this, do people have question about what the how to understand the time matrix, time map? If not, then I will continue to explain. Okay, wonderful. Now this is the A1 within interruption phase intersubject, because it's between one subject and the average others, and you loop through all the subjects and you average across all the maps. So essentially what this tells you is how similar between subjects neural geometry is due to the stimuli driving you to. And this corresponds to the interruption phase, and you can see that the A1 is overall pretty similar to each other during the interruption, which is expected because they're all listening to silent pauses. With that being the case, the way that we can know whether the pattern sustained during the interruption is sensitive to the stimuli or not is simply by mismatching epoch. So we can have the exact same temporal structure retained, but just scramble the matching of the pairs of interruption epochs, with the time being one interruption epoch versus another interruption epoch. So that with the diagonal cell here as an example, it's a match between TR number 118 versus TR number 324, which doesn't match in stimuli at all because it's not the same pair of epoch, and people are not listening to the same set of stimuli. But here, during the interruption phase, for A1, you still see a very highly lit up square, which is because they're still listening to silent pauses, even though it's different interruption epoch. And therefore, when you do a simple subtraction between the matching and the mismatching epoch, you will get a difference map that reflect whether the epoch matching over here has information that is selective to matching epochs. Now, I know that that must be confusing at some point. So do people have questions, or did I do a great job in explaining the logic? I did a great job? Oh, I'm flattered. Okay, great. You should be flattered too, because I don't think I did that good of job without rehearsing. So essentially what we're trying to see is whether the pattern similarity during the interruption phase is selective to the specific epoch that it follows. And with A1, you don't see the difference because it's not selective, and it's good. It's a good control to make sure that A1 is not sustaining past story-related information. And now comes to DLPFC. We looked at the same set of analysis with the DLPFC, and the expectation first here is that for the intact theory of mind condition, because people are doing a different task at each of, well, a different theory of mind question at each of the interruption epoch. And so if you do matching minus mismatching, they really should have a difference, because the pattern should be specific to the specific theory of mind question that they were listening to. The neural geometry should definitely differ across epochs. But for the intact pause and the scrambled pause condition, if you see the same kind of difference emerging from the matching and mismatching, then that would mean that the DLPFC sustained neural pattern is selective to the previous story segment. Otherwise, if it's flat like this, it means that it's task generic. All it's doing is just doing a task off state maintenance. So it's not even maintaining, it's just dropping to another state. Here's the actual data. So the intact tom condition, as expected, has a significant difference across the matching and mismatching epoch pairs, but the pause conditions do not, which means this working memory area is not actively sustaining story-related information. It is just doing a generic task on, task off switch. Now, any question related to this slide before I move on? Okay, cool. So the answer is no. The pattern is not specific to the prior content, and therefore it cannot be that the working memory is being actively sustaining your story content that could have explained why hippocampal did not predict individuals' memory in the intact pause condition. So to do a brief review, hippocampal at interruption onset predicts individual memory, and the dorsolateral prefrontal pause pattern is not epoch specific. So we are coming to our like proposed neural representation, passive trace somewhere in the DMN that can passively automatically sustain previously constructed context, even when your working memory is diverted elsewhere. And to do a first check, we have to see either a sustained activation or a sustained pattern throughout the interruption to first establish some sort of sustenance of neural traces. And we do see that for all of our pre-selected ROIs, with some satisfying both or some being just the sustained pattern. But that is not enough, as we just said. It has to be a pattern that is specific to the prior story that came. So we did the same set of analysis on each of these ROIs and tried to see whether there's a significant difference between the matching and the mismatching neural geometry between people. And we saw that the DPMC, as shown here, is significantly different. Which means that the pattern sustained during the interruption phase is selective to the prior story content. Now, just that is not enough yet because we have more stringent predictions for it to satisfy our hypothesis. So first thing is that this context, if this is the context that in our example that we said for the Harry Potter book about the world background, about his complex relationship with Amy, with his friends, with his life goals, and what is happening with the magic world, then that context needs to be built up across the entire course of your reading. And it needs to gradually evolve across the epochs. And so this is to say that across 18 story segments of a 15-minute long story, murder story, as you're trying to understand what is going on in the story, you first hear the opening scene where the husband is eating with the wife serves the food, but the husband is eating like he's mad. The wife picks up the phone call and he got furious about her deciding to pick up the call, which is from the sheriff accusing the man of potentially murdering a girl in the woods. And the husband says that they're crazy and he has nothing to do with this, like, et cetera, et cetera. And then over the course of the story, more information is revealed about what happened exactly around those days, during which the husband went on a hiking trip with the friends, and where they found that body, what they decided to do with the body, and seemingly that's what happened in their testimonies, and what did his friends say. So different angles and different information being revealed. And you're trying to understand through the story as a listener what is actually going on. Throughout this course of the narrative, when you have neighboring epochs, the same narrative context that you have understood should take up a bigger chunk of each other. So here, the gray area would be relatively still large in its neighboring segment compared to a longer distance where its relative proportion for the entire context that you have assembled should shrink over time. So this is to say that if this is the context that we are trying to capture, then the distance should predict how similar these contexts are to each other, with longer distancing should predict a reduced intersubject pattern similarity for their neural geometry linked to the narrative context. So this is the pattern that we predict to see if there were a narrative context sustained in this area. And this is a lot more stringent than just having this area select to the previous story content. Because you can imagine if the pattern sustained during the interruption, if it's just sustaining several TRs of like speech-related information, then it will forget what came way before, like 10 paragraphs before. You wouldn't have that information sustained during your current epochs. But this prediction is to say that you have to have that, and you have to have it in a specific way. So this is A1, the primary auditory cortex, where you should not be seeing this. This is anterior cingulate cortex, which is cognitive control, central executive conflict monitoring, which you do not have this. And this is the dorsal parietal medial cortex, which shows this gradual dropping of pattern similarity, which fits our hypothesis. Any question on this slide before we evolve to the next slide? All good? Okay, cool. So just having this is not enough yet. Well, the take-home message on this slide is to say that the parietal medial cortex pattern evolves across the environmental friendly light turns off every now and then. I have to move. So on this slide, the take-home message is that we did find a neural pattern that evolves across the entire narrative for the intact pause condition. And it seems to fit our prediction for what an evolving mental context is. And this pattern is sustained through the interruption. It is selective to the previous epoch. But just having this is not enough, because we said that this pattern needs to be passively sustained somewhat, so that even when your working memory is diverted elsewhere, it can still sustain that neural geometry, which is to say that despite interference with the intact theory of mind condition, it should still have its neural geometry somewhat matched to the intact pause condition. So if you look at the individual subjects in intact theory of mind condition, and match that to the group average template of the intact pause subjects for that epoch, it should still have a positive pattern correlation, which is the most positive with the shortest distance and with the same evolving pattern, with more distance seeing a drop in intersubject pattern similarity. With that being the prediction, here's the A1, here's the ACC, and here's the dorsal parietal medial cortex, which, again, the DPMC fits our hypothesis. So this is to say that the dorsal parietal medial cortex evolves across in even across the epochs, even in the intact theory of mind people. Now, great. Well, there's actually another thing. In the scrambled pause condition, these bars are flat. You don't see this trend. So that is the final control condition to make sure that this is actually a narrative context. And so to conclude, yes, we did find this passive trace, which shows that the dorsal parietal medial cortex activity, although it's not sustained through the interruption, it has a pattern that is sustained, that is selective to the previous epoch, that grows and evolves across the entire narrative and in ways that is only there for the intact story, not the scrambled story, and it's even there when your working memory is diverted elsewhere. So we find this process that we are going to name it the episodic background. The episodic background representation represents the background context that you have to understand your current input, as well as it serves as a function of spontaneously maintaining the trace on the background of your mind. It doesn't require your active control to hold it in place. With that being the representation that we already found, now say goodbye to that, and we need to establish a function for that. Because remember when we first asked the question of what happens when you come back to the interruption? What is helping you to re-immerse into the story and pick up where you left off? How are you able as a human to do that? Whereas state-of-the-art LLMs, which are so smart in doing so many things and still tragically fail when you have multiple topics spoken in the same thread of conversation. So we found this neural pattern being sustained through the interruption. And if you remember that we have a separate control condition of the continuous subjects that served as the ground truth, we are asking the question of when an interrupted subject come back from the interruption and start listening to each TR of the story, each time point of the story, compared to the answer key of the continuous subjects, control subjects, we can compute the pattern similarity at each TR to see how similar they are to the ground truth. And we can do that for each of the high-level areas that have been shown to be important for narrative processing, which includes the angular gyrus. And we can take these TRs, average across these TRs per subject to get an estimate of their alignment to the continuous, to the ground truth. And we can do the same thing for anterior cingulate cortex and other areas. And just to give you a sense of what the correlation is, yes, the answer is the DPMC pattern, the more it is sustained through the interruption phase, the more the person can realign their neural patterns to the continuous subjects. So yeah, this sustained pattern does serve a function. It helps your neural realignment to the ground truth understanding of the stimuli. But does this persistent pattern also predict your subsequent memory for the narrative? Here it is showing yes. Now, remember the previous little marker we implanted for suspense for why hippocampal activity weren't able to predict individuals' memory in the IP condition, the intact pause? Now here, the sustained dorsal parietal medial cortex neural geometry across the interruption phase is very saliently predicting individual memory for this group of people. So this answer finally closed up that suspense, and it also suggests that potentially there's a two-pathway process to support your mental continuity. One is based on hippocampus when your working memory is diverted elsewhere or when you are severely disrupted. And another more continuously that a DPMC-centered area of neural geometry sustenance through the interruption can help you keep that geometry in place for your return to the story. And so to summarize, we found that hippocampus is a very nice first pathway. The DLPFC is not doing much during the pause and for the silent pause conditions. And the episodic background process accounts for individual's memory, where hippocampus was not predicting the individual memory for. And for the function, that this sustained pattern predicts a higher neural pattern realignment with control group, and that it predicts individuals' subsequent memory for the entire narrative. So big thank you for listening, as well as people from this project. And now for whatever questions, people can freely ask whatever they're curious about.